Here are 10 space stories you can listen to in English. Now, let's get started. Tabby's star. What if a star, located 1,400 light-years away, began to flicker in a way never seen before? This is the mystery of KIC 8,462,852, better known as Tabby's star. This F-type main sequence star has shown unprecedented and irregular dips in its brightness, which have been observed by telescopes like the Kepler Space Telescope. While the transit of a planet typically causes a star's light to dim by about 1%, Tabby's star has experienced brightness drops of up to 22%. These dimming events last for irregular periods, from days to weeks, a pattern that cannot be explained by a simple planetary orbit. This highly unusual behavior has made Tabby's star one of the most puzzling stellar objects ever discovered. Early speculation even included the possibility of an alien megastructure, though this idea has found little scientific support. The leading scientific hypothesis is that the dimming is caused by a massive, uneven cloud of dust and debris orbiting the star. This material could be the remnants of disintegrated comets or planetesimals. Another, less favored theory suggests the star's light is varying intrinsically due to changes in its internal energy transport. Whatever the cause, Tabby's star remains a unique case of anomalous dimming, prompting further investigation into the dynamics of distant solar systems. Methuselah Star. Can a star be older than the universe itself? For a time, the star HD 14028, nicknamed the Methuselah Star, presented astronomers with this very paradox. Located approximately 200 light-years from Earth, this subgiant star is one of the most ancient objects ever observed. An analysis in 2013 using the Hubble Space Telescope estimated its age to be 14.5 billion years, with a margin of error of 0.8 billion years. This figure was startling because the accepted age of the universe is about 13.8 billion years. Further adding to its ancient origins, HD 140,283 is extremely metal-poor, containing only about 1/2050th the amount of iron found in our Sun, a key indicator that it formed in the very early cosmos before heavy elements were widespread. While the initial age estimate created a fascinating puzzle, the paradox is resolved by considering the measurement's uncertainty. The margin of error of plus or minus 0.8 billion years means the star's actual age could fall within the age of the universe, possibly around 13.7 billion years. Therefore, it is not definitively older than the universe, but rather a star that formed very shortly after the Big Bang. As a high-velocity star moving rapidly through the galactic halo, its chemical composition and age provide invaluable data for understanding the chemical evolution of the early universe and serve as a crucial benchmark for calibrating the ages of the oldest stellar populations in our galaxy. HE 1327-2326. Imagine a star with an iron content only about 1/300,000th that of our Sun. This is the reality for HE 1327-2326, one of the most iron-deficient stars ever discovered. With an iron abundance measured at FH equals -5.45, this star is an extreme example of a population 2 ultra-metal poor star, believed to be in its main sequence or subgiant phase. Located several kiloparsecs away, it has a mass comparable to the Sun. Its composition is a near-perfect sample of the primordial gas from which it formed. containing very few heavy elements forged inside previous generations of stars, making it one of the oldest survivors in our galaxy. However, the star's chemistry presents a fascinating paradox. Despite its extreme lack of iron, He 1327-2326 is comparatively rich in lighter elements such as carbon, nitrogen, and oxygen. This unique chemical signature provides crucial clues about its origin. Astronomers theorize that it was formed from a gas cloud polluted by the material from a single, very early supernova. The specific abundance pattern helps constrain the explosion mechanisms of the universe's first massive stars, known as population 3 stars, which have never been directly observed. Thus, He 1327-2326 serves as a chemical fossil, preserving the legacy of one of the universe's first stellar giants. BPM 37093. Have you ever imagined a diamond so large that it is the size of a planet? In the constellation of Centaurus lies a white dwarf star, BPM 37093, which is essentially a celestial diamond with a radius of approximately 4,000 kilometers. This stellar remnant is what remains of a star similar to our Sun after it exhausted its nuclear fuel. With a mass between 0.6 and 1.0 times that of the Sun, packed into a sphere roughly 2/3 the size of Earth, the tremendous pressure inside has caused most of its carbon and oxygen core to crystallize. This process has transformed the star's interior into a gigantic crystalline lattice, leading astronomers to nickname it Lucy, after the Beatles song Lucy in the Sky with Diamonds. Scientists confirmed this structure through astroseismology, a method that studies the star's natural vibrations to determine its internal properties. While the diamond star nickname is a powerful analogy, it is scientifically grounded in the fact that diamond is a crystallized form of carbon. The discovery of BPM 37093's crystallized core provided the first direct observational verification for a long-standing theory that white dwarfs solidify as they cool over billions of years. This crystallization process is not just a curiosity. It releases a significant amount of latent heat, which slows down the star's cooling rate. Understanding this effect is crucial for astronomers, as it allows them to more accurately calibrate the ages of white dwarfs, which are often used as cosmic clocks to estimate the age of star clusters and even our galaxy. WD 1145 plus 017. What happens to a planet after its host star dies? Located about 476 light-years away, the white dwarf WD 1145 plus 017 provides a dramatic glimpse into the violent end of a planetary system. This star is the first object where astronomers have directly observed solid debris from a destroyed planet transiting or passing in front of its stellar remnant. Researchers have detected multiple large dust clouds orbiting the white dwarf with a period of just 4.5 hours. These clouds cause incredibly deep and complex dimming events, reducing the star's brightness by up to 50% for durations as long as 87 minutes. This is interpreted as direct evidence of a planet or asteroid being torn apart by the white dwarf's immense gravity. The phenomenon witnessed at WD 1145 plus 017 is a process known as tidal disruption. The fragments of the shattered celestial body have formed a circumstellar disk of dust and rock that is slowly spiraling into the star. This makes WD 1145 plus 017 what is known as a polluted white dwarf, as its atmosphere becomes contaminated with heavy elements from the consumed material. This system serves as a unique laboratory for studying the final stages of planetary evolution, allowing scientists to analyze the chemical composition of the debris and, by extension, the makeup of a long-dead exoplanet. TRAPPIST-1. Just 39.6 light-years away lies a star hosting not one, but 7 planets similar in size to Earth. This is the TRAPPIST-1 system, an ultra-cool M-type dwarf star in the constellation Aquarius. The star itself is tiny, with only about 8.9% of the Sun's mass and a radius of 0.1192 solar radii, making it only slightly larger than the planet Jupiter. Its 7 known terrestrial planets, named TRAPPIST-1b through H, have radii ranging from 0.77 to 1.16 times that of Earth. They orbit their star in extremely close proximity, with orbital periods lasting from just 1.5 to 19 days, at distances of 0.011 to 0.059 astronomical units. Remarkably, at least 3 of these planets are located within the star's habitable zone, where liquid water could potentially exist. This compact arrangement is made possible by a stable orbital resonance, where the planet's orbital periods are related by simple integer ratios, preventing them from colliding. This unique composition makes the system an ideal natural laboratory for studying the formation of planetary systems and the potential for life around low-mass stars. However, the proximity to their star means the planets are likely tidally locked, with one hemisphere perpetually facing the star and the other in constant darkness. Furthermore, as a red dwarf, TRAPPIST-1 is prone to powerful stellar flares, which could strip away the atmospheres of these planets and pose a significant challenge to the development of life. Vega. Did you know that some stars are not perfect spheres? Vega, the 5th brightest star in our night sky, located just 25 light-years away, is a striking example. This A-type star rotates at an exceptionally high speed, completing a full spin in as little as 12.5 hours. This rapid rotation creates a significant centrifugal force that causes the star to bulge at its equator and flatten at its poles, forming an oblate spheroid. Consequently, Vega's equatorial radius is approximately 20% larger than its polar radius. This distortion also leads to a temperature gradient across its surface. Its poles are hotter, reaching about 10,000 K, while its equator is significantly cooler at around 8,900 K. Beyond its peculiar shape, Vega has played a fundamental role in the history of astronomy as a standard of measurement. For over a century, astronomers used Vega as the 0 point for the stellar magnitude scale, meaning its brightness was defined as magnitude 0.0. While modern photometric systems are now based on more complex physical models and measurements, Vega's stable and well-documented spectrum means it is still frequently used as a primary calibration standard for telescopes. This dual identity, as both a physically distorted object and a historical benchmark for brightness, makes it a uniquely important star. Sirius. Did you know that the brightest star in our night sky is actually a pair of stars? Located just 8.6 light-years away, the Sirius system, with its apparent magnitude of -1.46, outshines all other stars from our perspective. The main star, Sirius A, is a white A-type main-sequence star with about 2.06 times the mass and 25 times the luminosity of our Sun. Its companion, Sirius B, is far more extreme. It is a white dwarf, packing a mass of approximately 0.98 solar masses into a body with a radius of only 0.0084 solar radii, making it roughly the size of Earth. This compression results in an average density about 1 million times that of water. The two stars complete an orbit around each other every 50 years at a distance that varies from 8.1 to 31.5 astronomical units. The Sirius system is historically unique because it was where the existence of a white dwarf was first established. Long before Sirius B was visually confirmed, astronomers in the 19th century noticed a wobble in Sirius A's path, suggesting it was being gravitationally influenced by a massive, unseen companion. This dark companion was finally observed in 1862, providing the first concrete evidence for this new class of incredibly dense stellar remnants. This discovery was a landmark event in astronomy, not only validating theories of stellar evolution, but also proving that the effects of gravity could reveal objects otherwise invisible to telescopes of the era. Deneb. When you look at the summer triangle, do you realize one of its stars is an incomprehensibly distant beacon? That star is Deneb, an A2 I-type blue supergiant in the constellation Cygnus, which appears as the 19th brightest star in our night sky, with an apparent magnitude of 1.25. Its brilliance is deceptive. While it seems as bright as its neighbors in the triangle, Altair and Vega, Deneb is located at an immense distance, estimated to be between 1,400 and 2,600 light-years away. To be so visible from such a distance, its intrinsic luminosity must be enormous, ranging from 55,000 to as much as 200,000 times that of our Sun. This stellar powerhouse has a mass of approximately 20 solar masses and has swelled to a radius between 100 and 200 times that of the Sun. The significant uncertainty in Deneb's distance is a major challenge for astronomers and directly affects the precision of its other calculated properties. A distance at the lower end of the estimate, around 1,400 light-years, would imply a luminosity closer to 55,000 times the Sun's, whereas the upper estimate of 2,600 light-years requires a staggering luminosity of nearly 200 solar units. This range makes it difficult to definitively model its evolutionary stage and future. Nevertheless, its status as one of the most luminous stars known makes Deneb a crucial object for studying the life cycles of massive stars, serving as a prominent example of how a star's apparent brightness can mask an almost unimaginable scale of power and distance. Kepler-16. Have you ever imagined a world with two suns, like the planet Tatooine from Star Wars? The Kepler-16 system, located about 245 light-years away, turned this science fiction concept into a reality. This system is composed of two stars, Kepler-16a, a K-type star with about 0.704 solar masses, and Kepler-16b, a smaller M-dwarf with 0.205 solar masses. These two stars orbit each other every 41.08 days. Orbiting this stellar pair is a Saturn-sized gas giant named Kepler-16b, which has a mass approximately 0.333 times that of Jupiter. It completes one orbit around both of its parent stars every 228.8 days, making it the first definitively confirmed circumbinary planet. The discovery of Kepler-16b was a triumph of the transit method. The system is an eclipsing binary, meaning the two stars periodically pass in front of each other from our perspective, causing predictable dips in brightness of 0.15 and 0.02 magnitudes. Astronomers noticed additional, fainter dimming events that did not align with the star's eclipses. These transits were caused by the planet passing in front of one of the stars. By precisely timing these three separate types of eclipses, the planet's transit and the two stellar eclipses, scientists could unequivocally confirm the planet's existence and its stable orbit around the binary pair, solidifying the existence of Tatooine worlds in our galaxy.